Hello, everybody. Thanks for attending our number theory seminar. Today we have our special guest, Professor Dave Leep from the University of Kentucky, and he's going to talk to us about systems of quadratic forms over P. Thank you, Dave, for accepting our invitation.
Thank you for inviting me. I have not been to Brazil yet, and I hope this is just the first step.
Wow.
All right, so I'm going to be talking about systems of quadratic forms. Thank you for letting me speak in English. Please, you're welcome to interrupt me or stop me if you have any questions. It's not a problem, so I'll begin here. So I want to first make some definitions before I start giving any background or motivation. Just a few definitions here. So capital K is always a field, and I'm going to deal with a system of quadratic forms F1 through FR. So a quadratic form, of course, is a homogeneous polynomial where every monomial has degree 2. So we have R quadratic forms in n variables. We say that the system F, or script F, is isotropic over K if there's a vector A in Kn such that A is a 0 of each of the quadratic forms and A is non-zero. The 0 vector is always a trivial 0. So when we talk about isotropic, we always mean a non-trivial 0. And a system of quadratic forms is anisotropic over K if F is not isotropic. So the only 0 is the trivial 0. I want to deal with, I want to introduce the following definition, maybe unmotivated at the moment. U sub R of K is the largest integer n such that there exists an anisotropic system of R quadratic forms in n variables. And if no such integer exists, then we just say U sub R of K is infinity. All right, so the basic theme is this. So first we have a convention that U of K stands for U sub 1 of K. This is the classical U invariant of a field. So people in quadratic form theory study the U invariant. So that is, if I have one quadratic form, how many variables do I need to guarantee that this quadratic form has a non-trivial 0 over the field? So the U invariant, in a sense, this is the main motivation for maybe historical reasons. It's always interesting to know when can you find a non-trivial 0 over quadratic form. So let me start with examples here. The first thing is, over the real numbers, the U invariant of the real numbers is infinity, because as you can see, if I look at x1 squared plus ... x sub n squared equals 0, clearly the only way you can have a 0 is if each of the variables is 0, the trivial 0. More generally, in example 2, if K is a formally real field, and that means equivalent, either K has an ordering or equivalently, -1 is not a sum of squares in K. That's a theorem that is equivalent. Then the U invariant of K again is infinity, because you just look at the sum of squares. x1 squared plus xn squared equals 0 has only the trivial 0, no matter how large n is. So therefore, the U invariant is only interesting if we restrict to non-real fields, fields that don't have an ordering. So that's what I'm always going to assume from now on. All right, so starting with the easiest examples, if K is an algebraically closed field, the U invariant is 1, because it's easy to see that any quadratic form in 2 variables or more has a non-trivial 0, just because you can solve any equation, any polynomial over an algebraically closed field. More generally, instead of an algebraically closed field, it's not too hard to show that a field is quadratically closed if and only if the U invariant is 1. So here, a field is quadratically closed means K has no quadratic extensions. So obviously an algebraically closed field is quadratically closed, but there are other quadratically closed fields. There are lots of others. So one of the questions, so here, this sort of motivates a secondary question, although it is not written down here. One, given a field, what is its U invariant? But now another question is, what numbers can occur as U invariants? Well, we see that the U invariant can be 1. Okay, a finite field is the next easiest example for this question. If K is a finite field, the U invariant is 2. So this is the well-known theorem that any quadratic form over a finite field in at least 3 variables has a non-trivial 0. There are many ways to prove this. There are some non-trivial, there are some easy counting arguments, I think. All right, let's move on to other examples. If K is, this is example 6 now I'm up to. If K is a p-adic field, more about that later, but if K is a p-adic field, that means either QP or a finite extension of QP. Then it can be shown that the U invariant is 4. Any quadratic form in at least 5 variables over a p-adic field always has a non-trivial 0. Example 7 is for a number field, but of course, as I said above, I want to restrict to a non-real number field. So if K is a non-real number field, so that means K is a finite extension of the rational numbers and has no real embedding into the real numbers, then the U invariant of K is also 4. And so that's a more difficult theorem. It goes by the name the Hasse-Minkowski theorem. It actually requires a fair amount of work, the Hasse-Minkowski theorem. Over the rational numbers, it's still not easy, but over a general number field, you actually have to use some sophisticated results in algebraic number theory to give all of the details. Okay. So far, I've given examples of U invariants for sort of arithmetic fields, finite fields, p-adic fields, number fields. The next direction I want to go in terms of examples would be function fields over complex numbers and the real numbers. So in example 8, suppose K is a field having transcendence degree M over the complex numbers, and suppose K is finitely generated over the complex numbers. All right, so this is a typical function field that would occur in algebraic geometry. Then it's known that U sub R, now I'm talking about the U invariant for systems of R quadratic forms. It's known that U sub R of K equals R times 2 to the M. And note here, when I write M, I'm just going to write this here. I'm also allowing M greater than or equal to 0. So remember, transcendence degree 0 means an algebraic extension. Well, in the case of the complex numbers, there is no non-trivial algebraic extension, but later on. In example 9, suppose I have a non-real function field over the real numbers. All right, so this would be function fields. Such function fields occur in real algebraic geometry. If the transcendence degree of K over the real numbers is M, then the U invariant equals question mark. Okay, so this is completely, well, almost completely unknown. This is a really tough problem. Now, if M equals 0 or 1, then then the U invariant is known to be 2 to the M, i.e. 2 to the 0 is 1, 2 to the first power is 2. And you know, I should say a recent result, so I'm adding this right now. A recent result by Olivier Benoit proved that if M equals 2, the U invariant is 4. That proof is really difficult. Okay, that's a rather recent result in just the last couple of years. Yeah, okay, so that's example 9. So therefore, the examples so far are, again, those are from algebraic geometry and real algebraic geometry. And now moving to example 10. Here, well, this is now a mixture. Let's call this arithmetic geometry. If K has transcendence degree m over a finite field. So this is sort of the global field case, that, or a function field over a finite field. And if k is finitely generated, then it is known that the U sub r invariant, how many variables I need to solve r quadratic forms, is r times 2 to the m plus 1. If m equals 0, which means k is algebraic over f sub q and finitely generated, that means k is a finite field. This result actually follows easily from the Chevalier warning theorem. So let's see, if m equals 0 here, you can see that r times 2 to the m plus 1 is 2r. So the Chevalier warning theorem would say if I have r quadratic forms over a finite field in more than 2r variables, then there's a non-trivial 0. So this follows from sort of a generalization of the Chevalier warning theorem. Some of the reasons, especially in examples 8 and 10, why do these hold? That's coming up in a few minutes. Let's look at number 11, example 11. Now this is a much more difficult result. Suppose k is a function field over a p-adic field. Suppose it has transcendence degree m, and suppose k is finitely generated. Then it's a recent result, meaning during the last decade, in the last 10 or so years, that u sub r of k, the number of variables needed to solve a system to find a non-trivial 0 of a system of r quadratic forms over a function field of a p-adic field is equal to r times 2 to the m plus 2. Now, this is even in the case m equals 0, which means just an algebraic extension of QP, a finite dimensional one, so it's still a p-adic field. Then we're saying that it would be r times 4. So I'll just say 4r. So this was a problem that was open for many years. Originally, people like Birch and Lewis studied this problem in the 1960s. They got some partial results for small values of r, namely like r equals 2 and 3. More about that, I think, later in the talk. But the general result, it really, the next big step was taken by Heath Brown in around 2009 or 2010, where he showed this result right there. As long as, let's just say P is sufficiently large. And then I took that a little bit further and I was able to get the general result. So anyway, so for function fields over p-adic fields, it's much more difficult, but we know the value of this u sub r invariant. All right, so the next step, I just did function fields over the finite number, over a finite field, over a p-adic field. And next, what about a number field? So that's example 12. If K is a non-real field and has transcendence degree M over Q, so this would be a function field over a number field, and suppose K is finitely generated over Q, then the U invariant equals question mark. Hardly anything is known. We know the result for M equals 0. That's the Hasse-Minkowski theorem, which is already hard. But even for M equals 1, we don't even know. Let me just write this here. We don't even know if the number is finite. It is expected to be finite, but we have no idea. It's a really tough problem. So, all right. So I've given you sort of the main examples, the main motivating examples, namely fields that come up in number theory or arithmetic number theory or algebraic geometry, real algebraic geometry. Okay, now to go in a different direction, one can also study arbitrary fields. Arbitrary fields can be really arbitrary. There's lots of stuff that they can be really complicated. But on the other hand, if you're dealing with arbitrary fields, you have more room to play with, to play around, to search for odd counterexamples and stuff like that. Okay, so if we talk about sort of arbitrary fields, one of the main ideas is something that many of you are probably familiar with already. These are the so-called CI fields, or San-Lang theory. So let me make this definition here. Suppose I is any real number greater than or equal to 0. We say that K is a CI field if for all D greater than or equal to 1, every homogeneous form F in n variables of degree D has a non-trivial 0 defined over K whenever n is bigger than D to the I. Now, in this talk, when I'm dealing with a quadratic form, that's D equals 2. So my main interest is D equals 2, but the definition goes over in general. Well, a theorem due most to Lang, but really Nagata to put in the final touches, says this definition can be self-strengthened. If K is a CI field, and remember, that's a statement about one homogeneous form of degree D for every D, important. So Nagata shows if K is a CI field, then for all D, at least one, and all R greater than or equal to 1, every system of homogeneous forms, F1 through FR in n variables of degree D, has a non-trivial 0 defined over K whenever n is bigger than R times D to the I. So the point is, if you have a CI field, so that means that's a strong condition on one form, then automatically for free, you have information about systems of forms of degree D, all of degree D, for any R. All right, so let's look at, so what are examples of CI fields and why would they be interesting for this talk? Okay, so let's go back to some examples. So example 13, if you check the definition, it's easy to see an algebraically closed field is a C0 field. And in fact, I should have written down, if I didn't, it's if and only if. Algebraically closed, a field is algebraically closed if and only if the field is C0. So that's the definition. Finite fields are C1 fields, and this would follow from the Chevalier-Warning theorem. Now, why are the CI fields of interest? I would say it's the theorem coming up right here, because it allows for the following. Suppose K is a CI field, then any algebraic extension L of K is also a CI field. So in other words, if you know about forms or systems of forms over at K, you automatically know something for any algebraic, for forms over any algebraic extension L of K. Similarly, for a rational function field, this is number 2 right here, K adjoin X, where X is a variable, K adjoin X will be a CI plus 1 field. And if you combine 1 and 2 together, if L has transcendence degree M over K, then L is a CI plus M field. So the point here is, if you have a CI field, unexpectedly, you have all these hereditary properties. Suddenly you know about solving systems of forms, not only over K, but over an arbitrary function field of K. That's the origin of what some of the examples above when I was talking about function fields over the complex numbers, function fields over finite fields. Those results really follow from this theorem using the fact that an algebraically closed field is C0 and a finite field is C1. Let's see, that was number 3 in the theorem. What about number 4? To specialize to systems of quadratic forms, so number 4, the use of R of K is less than or equal to R times 2 to the I. That's just using the definition. Furthermore, if you have equality in number 5, if u sub r equals r times 2 to the I, so if you know exactly how many variables you need so that if you have one more than that number, you can solve a system of quadratic forms, then you get an exact number for every finitely generated function field. If L is finitely generated over K of transcendence degree M, then we have an exact expression for u sub r of L. So you can see that these CI fields are great for this problem. But there's no free lunch, as you know. So the fact is, it is usually very difficult to determine if K is a CI field for some real number I. So that's the problem. It's a great property, but how do you know if it holds or not? It's usually very difficult to determine. Okay. Now, as I said, in this talk, I'm specializing more to systems of quadratic forms. So it turns out just by altering the definition a little bit, it's very useful. So here we have, if K is called a quadratic CI field, if this inequality holds for all r greater than or equal to 1. So in other words, it turns out the right way to go. You have to think about this a little bit. To talk about quadratic CI fields, we don't want to talk about knowledge of one quadratic form. Turns out that's not good enough. If we make an assumption about systems of quadratic forms, then this is good, because then the theorem above that I just spoke about holds if the phrase CI field is replaced by quadratic CI field. So if we're only interested in systems of quadratic forms, we still have this wonderful notion of a quadratic CI field, and with then the hereditary properties of algebraic extensions and function fields and so on. All right, so as it says right here, we want to study u sub r of K for fields K. The best case is when K is a quadratic CI field, then, sort of for free, we get all these wonderful results. But as I say, even determining if a field is a quadratic CI field is often very difficult, other than the examples I gave you. So I want to say, listen, I guess it's coming later in the talk, but let me just say right now, is there a difference between these two concepts? Is it possible to have a quadratic CI field that's not a CI field? The answer is yes. If I can just squeeze that in right here, because I don't know if I said that explicitly later, I'll say there exist quadratic CI fields that are not CI fields. And in fact, in some sense, if you were really listening carefully, but if you're hearing this the first time, you might have missed it, I actually gave the answer. The example would be p-adic fields. P-adic fields are known to be, it is known that p-adic fields are not CI fields for any I. However, they are quadratic C2 fields. P-adic fields are quadratic C2 fields. This is the result I mentioned above, but not CI fields for any I. So these are distinct concepts. That's the point. Okay. So if we don't know that a field K is a quadratic CI field, what can we say about u sub r of K? So in other words, so suppose we don't know that we are in this really good case. What can we say? Well, there's still a lot we can say, although not nearly as much as we would like at the moment. First of all, there's an easy inequality. I'm not going to give the proof, but it's very easy to show in number 1 here. U sub r plus s is greater than or equal to this plus this. You just take 2 systems of quadratic forms and disjoint variables. Look at the definition. It's very easy to verify that. If I apply this to if I apply number 1 over and over to the case of 1, you see that u sub r of k is always greater than or equal to r times u sub 1 of k, just applying 1 many times, which is r times u of k. So we always have this lower bound that this u sub r invariant is always greater than or equal to r times u of k. It's an easy lower bound, and it seems that it's almost an upper bound. I'll say more about that in just a moment, but it's hard. I'll say it's relatively hard to find examples where this is a strict inequality. Okay. Now, in terms of this u sub r invariant, I said the best case, I'm going to rephrase something I said above. The best case is that u sub r of k is less than or equal to a times r for some real number a and all r greater than or equal to 1. Now, since we have this inequality from above, it's got to be the case that if we do have less than or equal to AR, the A has to be at least greater than or equal to U of K. So in this case, so if we have this inequality for some A, it just follows from the definition that K would be a quadratic CI field with I equal to this real number, logarithm of A to the base 2, logarithm base 2 of A. So the point is that I guess what I want to say here is this u sub r of k, the best case is when it grows linearly as a function of r. And then the question is, well, what is the constant? What is the constant in the linear growth? All right. As I say, that's the best case, but we don't always know if we have it. However, I will say right now, this is very strange. There are no counterexamples known where we don't have this kind of linear growth. It's just that it's often very hard to determine. So it might be the case that there's always some constant A where where this inequality holds for a given field. We don't know. What do we know? So we have this proposition here. U sub r of k is less than or equal to, well, I don't have linear growth. I've got quadratic growth. R times r plus 1 over 2. So r squared plus r over 2 times the u invariant of k. Furthermore, this inequality is optimal for r equals 1, 2, and 3, meaning, and I'm going to give an example of that in a moment. So this quadratic growth, so this was a theorem I proved really early in my career, a long time ago, and there have been no improvements since then. So here on the one hand, we cannot get better than a quadratic bound, but we have no counterexamples that it's not always a linear bound. Very strange. Let me give some examples to show that this is optimal for r equals 1, 2, and 3. So here, in example 15, suppose K is the quadratic closure of Q. So it's the smallest subfield of the algebraic closure of Q such that every element of K is a square. It can be shown that the u sub 1 is 1, u sub 2 is 3, and u sub 3 is 6. Sorry. And that corresponds to equality up above for r equals 1, 2, and 3. So in particular, K is not a quadratic C0 field. Is K a quadratic C1 field? We don't know. So for 4 quadratic forms, let's see. The proposition says 4 quadratic forms in 11 variables always have a non-trivial 0, 1 more than 10. Is it the case that 4 quadratic forms in 9 variables over the quadratic closure of Q? Do they always have a non-trivial 0? We don't know. So in fact, I'm sort of restating this question. There is no example known of a field K where this U sub R invariant is greater than R times 2 times the U invariant. So sometimes it's bigger than the U invariant, but we don't know any example where the constant here would be bigger than 2. So kind of strange. All right, this result I just mentioned leads to the following. What about an algebraic extension? Suppose L over K is a finite algebraic extension of degree R. Then the U invariant of L is less than or equal to R plus 1 over 2 times the U invariant of K. And this inequality is optimal, again, for R equals 1, 2, and 3. Because with 3, you get 3 plus 1 over, we can say it here. If K is the quadratic closure of Q, there are cubic extensions. It is known there are cubic extensions with U invariant equal to 2. A lot more is known, but this is enough for this. And that's equal to 3 plus 1 over 2. So this shows that when R equals 3, you can have equality. Now, in this example 17, this is tricky. I'm claiming there exist examples, K and L, where L is a quadratic extension of K, and the U invariant of L is 3/2 times U of K, where U of K is 4 and U of L is 6. This takes a lot of work to construct. So I'm not writing this down here, but here's the thing. In terms of the so-called well-known fields or the well-behaved fields or the fields that seem accessible, the U invariant tends to be a power of 2. For a long time, it was not known whether the U invariant could be a number other than a power of 2. It wasn't until the late 1980s when Merkuriev first constructed an example of a field with U invariant 6. And I guess it was in a joint paper. Merkuriev and I published a joint paper in the 90s where we constructed a quadratic extension where the U invariant goes up by a factor of 3/2, such as 4 to 6. It says this takes a lot of work to construct. Well, it does. It's one of these huge fields, and you use Zorn's lemma and a lot more, many more ingredients. Yeah, but we don't, let's see, do I say it here? No. But again, just to stress, we do not know any example where the U invariant of an algebraic extension goes up by more than 2 times the U invariant of K. Now, I want to give some other examples here. Let's see, time is going by quickly. Okay, I should speak quickly. The U invariant of a power series field. So K power series T, that's the fraction field of the field of formal power, of the ring of formal power series. It's known that the U invariant doubles here. However, so the comparison, so this turns out to be relatively easy. However, if the U invariant is finite, it is completely unknown whether the U invariant of the rational function field is finite. So there's no, we know very, very little. This is a very difficult object to get a hold of. So we don't know whether that's even finite. Here's just one example. I'm going to skip that. This is, okay, now I want to give another set of interesting examples. Suppose P is a prime number. K is called a P field if every algebraic extension, finite algebraic extension of K is equal to a P power. So that would mean the absolute Galois group of the field is a P group. The only extensions, the only degrees of finite extensions are powers of P. So for example, an algebraically closed field is a P field for every P trivially because p to the 0 is 1. A real closed field, such as the real numbers, is a 2 field because the only algebraic extensions have degree 1 and 2, so powers of 2. There do exist non-algebraically closed fields for every prime p. There are ways to construct them. So there's this interesting theorem here. Pfister proved number 1, if k is a p field for some prime number p different from 2, then k is a quadratic C0 field. And so I proved a partial converse. If the characteristic of k is 0 and k is a quadratic C0 field, then k must be a p field for some odd prime p. So it's a Galois theoretic characterization of quadratic C0 fields. So that's a nice result. If the characteristic of k is not 0, the status of 2 is not fully known. I'll just say there are partial results, but I won't go into that. All right, now let's move to p-adic fields and similar things. If k is a p-adic field, which means a finite extension of qp for some prime number p. So that's the definition of a p-adic field. There's a theorem, and I mentioned before, a p-adic field is a quadratic C2 field. So that was the result I mentioned above. Heath Brown took the major step, and then I finished it, and I was able to prove that p-adic fields are C2 fields. So now what about, there are generalizations of p-adic fields, and the idea is to talk about evaluation as follows. And let me scroll up here. So just some basic definitions from valuation theory. V, a mapping from k to the integers union infinity. Suppose that's a valuation, and assume that there exists an element pi in k such that v of pi is 1, so that this map is surjective. As a reminder, or I'm telling you, the definition of evaluation is that the valuation is infinity if and only if a is 0 and numbers 2 and 3 hold. So that's the definition. And there are certain objects associated to evaluation. There's the ring of integers, denoted O sub k. And it's those elements in k whose valuation is non-negative. M sub k is the unique maximal ideal inside the ring of integers. It's those elements whose valuation is greater than 0. And I didn't write this here, but those with valuation 0 in the ring of integers O sub k, those are the units. So M sub k is a maximal ideal and it's a principal ideal generated by pi, and lowercase k or little k is defined to be O sub k mod M sub k, and that's the residue field of this valued field. So these are the 6 pieces of information associated with a so-called discrete valuation on k. So I'll just give 2 examples here. K double bracket x, the ring of formal power series, and then k double parentheses x is the fraction field of k double bracket x. So we can define evaluation. It's maybe you know this already. If G is this formal power series here, V of G is equal to M if the first M coefficients are 0 and A sub M doesn't equal 0. And you can extend it to the field if you say V of X, if you say V of 1 over X is minus 1, this gives a valuation on K, the fraction field. And with O sub K, the ring of integers is the ring of formal power series. Pi, we can take pi to be X, and the residue field is little k, the coefficients. And then the second main example would be actually say the QP, the p-adic numbers, or really any finite extension. In this case, the ring of integers is Z sub p, the maximal ideal is generated by the prime number p, and the residue field is F sub p, the finite field with p elements. Well, a discrete valuation induces a metric topology on K. I didn't write down how you do that, but it does. So we say that K is complete with respect, in examples 21 and 22, one can show that K is complete with respect to this induced metric. So we say that K is a complete discretely valued field in that case. So a big problem would be this. Suppose K is a complete discretely valued field. So it's a generalization of these two main examples I gave you. Can we express the U sub R invariant, this for systems of quadratic forms? Can we express the U sub R of capital K in terms of U sub R of the residue field little k? Well, there are some easy cases. I mentioned above this result, so that's the case R equals 1. One can also show, but I'm not showing it here, that for R equals 2, it's also the case that the use of, for a system of two quadratic forms, the number of variables you need is greater than twice that number over the residue field. So we have this relation here. It would be conjectured that in the case of, again, a complete discretely valued field, that that U sub R of K, capital K, is always 2 times U sub R of little k. Now, I wrote conjecture in quotation marks because this is not an official conjecture. I call this a working conjecture. It would seem that this is a reasonable result, but maybe we don't have enough examples to say this. Now, I've written down here proof strategy. How do you even deal with this? Well, in one phrase, it's use Hensel's lemma, but let me explain. So the proof strategy is this. Suppose I have, sensitive iPad. Let's go back here. Suppose I have F1 through F sub R quadratic forms. Just by multiplying through by an appropriate constant, I can assume that F1 through F sub R all have integer coefficients because there are only finitely many coefficients involved, so I can multiply through by an appropriate element of the field. So when they all have integer coefficients, I can reduce mod the maximal ideal. So F1 bar through FR bar denotes the reduction of F sub I over the residue field. In other words, you're looking at it mod M sub K, mod the ideal M sub K. The proof strategy is try to show that F1 bar through FR bar, that this system has a non-singular 0 over K. So let me define that. So the definition of a non-singular 0 would be this. You form the so-called Jacobian matrix. So you look at the R by N matrix, whose ij entry is the partial derivative of F sub I bar with respect to X sub j. So there are R forms and N variables. Let P be any point in Kn. So in other words, A1 through An, where each AI lies in K. And take J of P. So in other words, evaluate each of these partial derivatives at P. So I'm going to get an R by N matrix. So we say that if P is a 0 of F1 bar through FR bar, oh, I left this out, my God. If these are all equal to 0 and J of P, this Jacobian matrix at P has rank R, then P is called a non-singular 0 of the system. Okay, and why do I want this? Because this proposition, this is a form of Hensel's lemma. If P is a non-singular 0 of F1 bar through FR bar, then there exists an element C over the ring of integers such that it's a non-trivial 0 of F1 through FR, and C is congruent to A mod M. So in other words, Hensel's lemma lets you sort of approximate or lift a solution in the residue field, if it's non-singular, to a solution over the ring of integers. This is also known, especially in the case of one form, this also goes by the name of Newton's lemma or Newton approximation, stuff like that. I wrote here, this is a form of Hensel's lemma. Well, back to the original problem about a system of quadratic forms over a complete discretely valued field. I'm going to say that if R equals 1 or 2, and n is bigger than this number here, this strategy works. You can find, here I say, if R equals 1, it's not too hard to argue that there's a non-singular zero. If R equals 2, the same strategy worked, but it requires much more work. Burge, Lewis, and Murphy first proved this in 1962. So it goes back a long time, but yeah. Now, for R equals 3, Burge and Lewis, I didn't write this down here, but Burge and Lewis did a lot of work. They came up with something really complicated, and they kind of pushed it through, but it was a real mess. Here's an example of a theorem I proved. Suppose we have a complete discretely valued field. Assume the residue field is infinite. Assume we have this inequality for all r greater than or equal to 1 and some positive real number a. Then we have u sub r of k is less than or equal to 2ar, which is what I want, but I'm adding something, plus m of r for all r greater than or equal to 1, where I actually have a precise value. But what is important to realize here is this quantity, m of r, is independent, completely independent of the complete discretely valued field. So in other words, no matter what field I pick, no matter what complete discretely valued field I pick with infinite residue field, I get this inequality, but there's always, for a given r, plus this fixed constant. Constant depends only on r. It's kind of interesting. Since I started a little bit late, I'm going to go just a little bit late, the same amount. I want to make some additional remarks on Hensel's lemma and a related result. It's kind of interesting. I stated Hensel's lemma, but I didn't say anything about it. You know, how does it work? Well, in the proof of Hensel's lemma, what you do is this. One constructs a sequence of points, P0, P1, P2, etc., such that 3 conditions hold. The first point, P0 bar, when I look over the residue field, it's the original P that I wrote above. Pi plus 1 is congruent to P sub I mod this power of the maximal ideal. And f sub j of P sub I is congruent to 0 mod this power of the maximal ideal for every j. In other words, in the proof of Hensel's lemma, what you do is you gradually construct better and better approximations for a 0. You find a 0 to this whole system, mod m squared, mod m cubed, mod m to the 4th, etc. And then what Hensel's lemma does, if you check the details, you show that the sequence P sub I guess I should put, it's the limit of the sequence, exists because it turns out the P sub i's form a Cauchy sequence with respect to the metric. And because k is complete, it converges to some p prime. And then using continuity of the polynomials f1 through f sub r, so polynomials are continuous in this situation, it follows that p prime will actually be a non-trivial common 0 of our quadratic forms f1 through fr. So that's the way Hensel's lemma works. It's really a wonderful application, mixing point set topology and this material here. Well, what's interesting, Greenberg proved a theorem that gives a similar result with weaker hypotheses, which I want to mention. Suppose we have almost the same situation. Suppose P0, P1, P2, P3 is a sequence of points satisfying 1 and 3. So 1 and 3 So in other words, but I'm not assuming, I'll do it like this, but I'm not assuming that these points are congruent mod powers of the maximal ideal. They are not, they do not form a so-called coherent sequence. So we are not assuming that. Suppose they satisfy 1 and 3, then F1 through FR is still isotropic. There's still a non-trivial common zero. He used a rather sophisticated proof. And in the case of characteristic zero, a Kneser, let's see, so Greenberg's theorem is, say, mid-1960s. Kneser gave a proof in the late 1970s for fields of, well, if the characteristic of the ring is zero, which is incredibly clever and much more, very, very elementary, not easy, but very elementary and very clever. Now, yeah, it's kind of, it's an interesting topic to pursue. Now, in the case when the residue field is finite, as I write here, the two results are the same, because if you have properties 1 and 3, it turns out using the finiteness of the residue field, one can extract a subsequence that does satisfy property 2. And then you can apply the usual Hensel's lemma. But this argument doesn't work if K is not, it does not work if the residue field is not finite. Furthermore, Greenberg does not require that the valuation be complete. He only assumes that you have a Henselian valuation, which I will not go into, and one additional technical hypothesis that I'm not going into, if the characteristic of K doesn't equal 0. So, you know, I had more material, but I think this is a good stopping point here. I will stop here and take any questions if you have any questions.
Thanks, Dave, for this wonderful seminar. Well, you left a lot of problems here.
Oh, yeah.
It was
Yeah,
a
these are wonderful problems.
Yes, wonderful problem. And well, are you working one of them now? So
No, I'm working on all of them.
Are you working all of them? So it's a
Yeah.
big discouragement for us.
No. Please, you should feel free to work on them. And the truth is, if any of you are seriously interested, you know, graduate students, whatever, you're welcome to email me. You're welcome to email me. I would be happy to communicate. I like these problems and I like these results very much. So any of you are welcome to email me. Please write in English. I apologize. And but other than that, I'd be happy to communicate with you.
Wow, this is wonderful. Well, there are questions and comments.
Yeah, I'm not very good at.
Yeah, there is a question here. Let's see if I
I
can.
do something, or are you going to speak? I see a hand, but I don't know what to do with the hand.
Tel, can you speak?
Yes, can you hear me?
Yes, I can hear you.
Thank you, Dave. It was a very nice survey talk. It was
Thank
excellent. Thank you very much. I have actually a curious question about absolute Galois groups that you mentioned before.
Okay, I don't guarantee an answer, but go ahead.
Thank you. About quadratic CI fields. I believe that it's known that if you take an absolute Galois group in general, almost in general, at least for small i's, if you look at the maximal pro-Pisa group of the absolute Galois group, it has a cohomological dimension at most I.
Yeah.
At least for 0, 1, 2, that's okay. So my question is, in general, if for any quadratic CI field, we have this property that the maximal pro-Pisa groups have cohomological dimension at most I. Is this known?
Well, I would say Okay, so I can sort of give an answer. Okay, suppose I've got a quadratic CI field. So in particular, it means that the U invariant of the field is less than or equal to 2 to the I, and the same thing for every finite extension. So in fact, something can be said. What I'm about to say is at least 90% true. It will be enough for you to look further, you know, it'll be enough for that. So what this means is if you're willing to use this very difficult theorem originally called Milner's conjecture, but now it's a theorem that relates Milner K-theory with Galois cohomology and some certain objects in the Witt ring of quadratic forms, yeah, then it's going to follow that I don't know, you see, so I don't know a lot about the cohomology, but the two cohomology, the two cohomological dimension is at most I, or is less than or equal to I. So something like the two cohomological dimension. Does this make any sense to you?
Yes, yes, absolutely.
Yeah, and I think I've said enough words so that if you want to pursue this, I think you could, because that's the connection.
Yes, and the follow-up question would be not about maximal pro-p subgroups, but maximal pro-p quotients.
Ah.
Is there anything that we can say? Well,
no, because let's see, because a quotient, the quotient, one of these, say, take the absolute Galois group modulo something or other, that would correspond to the Galois group of, say, some finite algebraic extension, right? And, well, I mean, let's, if I can let P equal 2, yeah, so what is the Galois group of, oh yeah, say take the quadratic closure of the rational numbers over the rational numbers. Yes. You know, there has been work done, and I'm not the right person to ask, but I could name some names, because in fact, these groups can be rather complicated. They are two groups, but these two groups are not easy two groups. They are rather complicated. You know, there's this interesting paper. Is it Jan Minach and Michel Spira? And Spira, he's Brazilian actually, right? Do you know him?
Yeah. Yes, from Universidade, yes. But I was not aware about the paper.
Yeah. So this paper, oh, I'm going to say it's 1990s, but it's Minach, M-I-N-A-C. He's in Canada.
Jan Minach, yes. I know.
Yeah, Jan Minach. Okay, well, okay, fine. And yeah, they have a paper where, oh, they address some aspects. You could go there.
Oh, excellent. Thank you very much.
Yeah.
And again, thank you for the talk.
Sure thing. You're welcome.
Any other question or comment? Let me ask you one thing. Since we have many students here, would you, if someone is trying to study this, would you point out some, oh, read this paper, and this paper, and you have this general understanding of the area or language, and now do you have this kind of information that you could give us?
Okay, you are talking about systems of quadratic forms,
yes,
right?
Yes.
Okay, so let me mention a few things. Okay. There's a book, there's a textbook by Pfister, Albrecht Pfister, in the London Mathematical Society, lecture notes in mathematics. It's something like volume 217. It's 1995.
Okay.
And so this is a book about quadratic form theory. His chapter 9 is about systems of quadratic forms. One of the topics he considers later, which is something I did not address. I will be very brief here. Remember I said, oh, I will only consider non-real fields, otherwise it's not interesting. Well, okay, so that's not completely true. There is a modified U invariant that can be defined for formally real fields where you restrict to quadratic forms such that the quadratic form has zero signature with respect to every ordering of the field. Okay. Pfister starts to develop a theory of systems of quadratic forms for formally real fields. I guess it's in the latter part of chapter 9 of this book. That theory has a lot of room for polishing. It's not in great shape. Okay, now as for non-real fields, okay, there's the first part of chapter 9, and it's going over some of the material I did here. Well, okay, so there are my papers. I have a paper in 1984 called something like, a creative name like Systems of Quadratic Forms. It's a 1984, if you look this up. I have a paper, I guess it's published in 2013 in Krella. Oh, both of them are in Krella's journal. 2013, Systems of Quadratic Forms. I don't know what the title is, but it's very close to that, 2013. And then unfortunately, I have a lot of work which is unpublished. I regret to say, I'm a bad person, okay? And yeah, that's, so I could suggest more problems, and I could sort of send my private notes and my preprints. I've got lots of things typed up in preprint form and so on. But yeah, so that's where what I would say so far.
Oh, but that's excellent. You made this wonderful introduction to the theme and gave all this reference. Well, the table is set for all grad students to grab all of this, isn't it? Well,
yeah.
Let's thank again Professor Dave Leep. Thank you very much, Dave, for this wonderful lecture.
Thank you.
I thank you all for attending this meeting, and we'll see you again next Wednesday. Bye-bye. Thank you, Lee. Thank you.
Thank you. Thank you.
Bye-bye.